enough of the economics and the stock flow consistency. So let's see a little bit of the climate and how they interact together. So this is a very, not yet. Yes, to introduce that, the next slide is going to start with emissions, and then there's going to be a long series of logical steps that follow from emissions and how they influence the climate and so on and so forth. But just to set the scene, how much emissions do you think, because it's good to have, orders of magnitude. We are quantitative people, so we started with the orders of magnitude of the risks, the trillions in losses, and then how much investment is to be done every year, how much investment is being done. So I like to put rough numbers into these things. So does anybody know what is the rough number for emissions per year now, for example? I just want an order of magnitude in terms of tons of carbon. How many zeros I'm looking for? So I have a good rule for you to remember. So because it's large numbers, right? But also there's large numbers of people in the planet. So how many people are there in the planet? What's the order of magnitude? Billions, right? So they're like 7 billion or something. Okay, yes. So the order of magnitude for emissions is that each person on average emits a few, so 1, 2, 3, 4, 5 tons of carbon. On average, each person contributes to about 4 or 5 tons of carbon. So emissions are in billions of tons, so they are in gigatons. So if you have to remember, when you read in the newspapers, you already know what the ballpark is. Okay, so that's what it is. So we're talking about billions of tons. So if you have like 7 billion people, 40 divided by 7, that's what I said. It's of the order of 5, 6, 4, depending on which country you are. Okay, and that's the path of emissions from 2000. You could continue the graph here. It's slightly higher, and the hope is that eventually it starts to go down. We're going to see many projections for that later. Yes?
Is there some expected threshold that you cannot pass?
Not for emissions, but for accumulated emissions. That's the carbon budget that I mentioned in the beginning. And yes, it's so. So from the antiquity all the way to the beginning of the Industrial Revolution and a few years later, the total amount of emissions globally was about 500, so 10 times larger than this, right? 500 gigatons. And then they've been steadily increasing, and now we are at the point of, each year we put 1/10 of what had been accumulated for the previous history of humanity. And the total budget is just, a couple of times that. Right, so we don't have too many more years. So we might have, about 5, 6, 10 years of those rates, and then it needs to go down. But what is the budget? I mean, it's not something that if it immediately hits that, then everything is gonna collapse. So it's not a threshold like that. Maybe to answer that question, we need to see the rest of the climate module, because you're going to see how the emissions affect everything else, and in particular temperature, and what you want is to maintain the temperature within a certain threshold. But what you would like is to maintain the temperature below 2 degrees from pre-industrial levels, and because of that, there is the physics of how emissions contribute to that, and that would tell you an amount of emissions that you could have cumulatively. It's almost exhausted, right? So it's like almost 80% exhausted. That's what I said right in the beginning, that for sure you cannot continue exploring fossil fuels that are underground, because the amount of fossil fuels that are underground, if you take them out, the emissions that it would produce would go above the budget by a large amount. All right, so there's no uncertainty in that. You cannot. So at some point you're going to have to. So that's why the stranded assets will come into play. Right? Yes.
Perhaps it's a sad question, but what is the amount of carbon dioxide in the atmosphere?
Well, that's a good question. I have to check. Let's check after the break. But it's yes. That's right. Yeah. I know what you're saying. I mean, this is not negligible, right? This is comparable to, so it isn't ballpark, but maybe it's half, maybe it's a third, I don't know. Yeah. Okay. So this is the breakdown of percentage of CO2 emissions per country. So China, of course, is the largest emitter now, followed by the United States. The difference is that since that was calculated in 2017, China has taken dramatic measures to decrease, whereas the United States, as you know, has pulled out of the Paris Accord. So, you know, this picture might change in a few years. So this is the slide that I say is very heavy, but in the next half hour or so, I want to explore line by line in this slide and try to understand what's going on there, and then we move to the next module in the climate. So the first one has to do only with emissions. So let's just go slowly. So total emissions are going to be separated by two components. So one is industrial emissions. So that's the part that we're going to try to address. So this is the part of the emissions that can be addressed by policy, right? And because industrial emissions is going to be the result of your potential GDP. So how much is there, and then if because remember, the potential GDP is what you do, and then you divert part of that to abatement, and then part of that is damage. But you did that already, so you already emitted. So there's this Y0 that then gets multiplied by a sigma. So forget about this factor for a moment. So there's a relationship between how much things you do each year and how much emissions they generate. And that relationship is captured by sigma. And sigma is the carbon intensity of the economy. So just like, you know, how factories make things and how much emissions are being generated by that. So that carbon intensity is decreasing in time because technology is improving and we're becoming less and less carbon dependent. But so it's decreasing according to a function like this, where the rate of increase of that is itself decreasing. So it's a kind of function that does that. It's a logistic function going down. So eventually, there's going to be a very low carbon intensity. But the point is that eventually could be too late. So we will get to a point where no matter how high the production is, we're going to be emitting very low amounts of carbon, but that could happen too late. So to accelerate that, so this is why I said before you put this 1 minus n, it would just be sigma times y0. So do nothing, and just the normal pace of technology will guarantee that we become less and less carbon intense. But you want to accelerate that. So you want to do, in addition to that sigma, some emission reduction. So the emission reduction is n. So n is going to be anything that firms actively try to do to reduce their emissions. So they're going to be trying to invest in that to reduce their emissions. And how are they going to be doing that? They're going to be spending. They're going to be spending some amount of money, A. So this, I'm going to be jumping back and forth in all the lines of these slides, but hopefully if there's anything that I didn't cover, you let me know. So again, industrial emissions are things that are coming from the firm sector. If they don't do anything, there is a natural rate of decline that is given by sigma, but that might be too slow, so you want to accelerate that, so you want to do emissions reduction. But for each unit of emissions reduction here, there is a cost. And the cost has to do with many things. The cost has to do with the current value of the intensity of the economy. It's going to be, as the intensity goes down, naturally, it's going to be easier to reduce emissions. The whole economy is becoming more carbon efficient. But it has a factor theta, so this factor is the convexity of the cost. And it could be like the first amount of emission that you can do is cheap, but to achieve more and more reductions, then is more expensive. So this is a convex function, right? It's not linear. So we're going to see how this theta coefficient, we're going to do a lot of sensitivity analysis with those coefficients later. But crucially, it's going to depend on the price of the backstopping technology. So emissions reductions are primarily done by changing the way to do something into doing something else. So instead of using fossil fuels, using wind or electricity or other different technologies, solar panels and so on and so forth. So the price of that, as it goes down, it will affect how much is being spent. So imagine if the price of solar panels go really low, then you can retrofit your entire factory with a lot of solar panels, and you're going to be using less fossil fuels to run it, so you're going to reduce your emissions. So the cheaper the backstop technology, the cheaper is your abatement cost for the same unit of emission reductions that you want to do. Are things making sense so far? So I went from there to there. But then what is the backstop technology? Well, the backstop technology is itself something that is not directly controllable by decisions of firms, how much to invest and so on, because it also depends on the pace of technological improvement. But you could try to alter that by doing more R&D and research. So we're going to be changing that too. We're going to be controlling that as a sensitivity parameter. But the assumption is that the backstop technology is decreasing. The price is decreasing in time, and we're going to see a few examples. And for most technologies, it is the case. Batteries are getting cheaper, solar panels are getting cheaper, installing windmills is getting cheaper, and so on and so forth. But we're going to see if they're getting cheaper at a sufficiently rapid pace. And then, a key incentive to do all this is then the price of carbon. And we're going to see in later slides how that plays a role, or maybe I can put it on the board. But the idea is that firms are being charged a carbon tax on the emissions that they actually do. So there's a carbon tax that is equal to the price of carbon times the amount of emissions. And this is the real value of the carbon tax. So you now, because the price of carbon in all my slides is going to be in constant dollars. So it's going to be inflation-adjusted price of carbon. So I multiply here by the actual price of goods. So that's the carbon tax that they pay. The abatement cost is something that they would also pay, but the abatement cost then, the idea is that they want to reduce their emissions. So this is PC times sigma 1 minus n y0. And abatement cost is sigma p for the backstop technology n theta divided by theta. And the more they spend on abatement, the less they would pay in carbon tax, because then emissions would go down. If n goes up, emissions go down. So what they want to do is to choose n, so this is a simple optimization, so choose n to minimize the sum of the carbon tax and the abatement cost. So when you do mean over n of carbon plus abatement, then you obtain that n that is there on this slide. That's the chosen rate of emission reductions that the firm will do, right? And you see that depends, because the carbon price enters here and the backstop technology enters there, depends on the relationship between the two. And in particular, the more expensive carbon is, there is more of an incentive for the firms to be doing this emissions reduction, because the carbon tax term goes up, whereas the abatement cost doesn't go up. And also the cheaper the backstop technology, also the more incentive the firms do to reduce emissions. So n depends on the ratio of the two, and of course with that convexity factor adjustment. So this just tells you how carbon prices enter into the picture as an exogenous variable that it's put on by the government to accelerate the emission reduction. Does that make sense? So now do we understand everything that it's in this slide? Yes? Sorry, say again? Oh yeah, and the emissions land is the things that you cannot touch by industrial policy. So it's the stuff that comes from other, and that is also assumed to be decreasing in time. Sorry, it's assumed to be increasing in time but plateauing. It's assumed to be that rate. The industrial emissions are larger. Is the dominant? Yeah, is the dominant component. Okay. So do you understand? Yes. Yes, that could be part of, so a reduction in emission could be in the form of sequestration. So yeah, that's included in that. But that costs money too, so that's part of the abatement cost. So this is an average abatement cost for all sorts of technologies that the overall result is to reduce the net emission rate. So this is the net emission, which is what is emitted minus what's sequestered. Yes? For what? No.
Because unfortunately, that's something that we all know. Some countries.
No, that's right. So that's a good point, and it's, there's also now an incentive for governments to have a very good way to measure emissions of the different polluters if they're going to have a carbon tax. Of course, the tax is just like any other tax. If you have no way to enforce the tax, then it's useless, right? So there could be tax evasion for carbon tax. What's tax evasion for income tax? You lie about your income. And then it's the job of the government to verify that your income is true by looking at things like your assets and your way of life. If you're a drug dealer, with millions of dollars flowing around, and then you only declare that you have a minimum wage, then of course there's something suspicious. So same thing here. A carbon tax is a tax on emissions by a company, and if the company lies about the emission, the government is to check, their balance sheets, their production, their sales, and match with data that they have about that type of industry and what's the average emission for that type of industry, and if they are not declaring it correctly, then they go and have to investigate. But yes, it's obviously something that the governments have an incentive to monitor very well. Yes?
So time here should matter because introducing a carbon tax does not mean that the industry will adapt.
Yeah, time, all these variables have a time dependence that is not explicit in here. And for example, so here is my graph of the intensity, the carbon intensity sigma over time. So it's a very good question because it allows me to move the slides along. That the questions that get me stuck in the same slide, but the questions that I can progress. Do both. So yes, you see here the sigma over time, the carbon intensity is going down. This is a projected carbon, a possible carbon price path. So this is entirely by policy. And this, I didn't pick this at random. This is one of the paths that is recommended by the Carbon Commission, the Intergovernmental Carbon Commission coming from the UN. So a steep increase in price until about 2020, and then a less steep, because you want to do, cut emissions up front as much as you can. So, but also the industry needs to know that there is a kind of a sort of predictable path for carbon, because that will determine all sorts of investments that they would do. But the point is, all of this has to be, ideally, sort of promoted policy, public policy. The government, and there is, so Andrea has an ulterior motive to be asking this question, because we're trying to develop a derivative that will protect industry against changes in the publicized carbon price. Because, suppose that a government now, like Bolsonaro's government, declares that they're going to have this price for carbon, and then all sorts of industries adopt policies that would take a lot of time to develop, to implement, based on that predictable path of carbon. And then another government comes in and does something completely different, and the most likely thing for governments to do is to drop that. because carbon is then increasing in price. They will have some lobbyists saying, this is expensive, it's a tax, it's a tax, it's a tax. There's always some crazy libertarian saying, it's a tax, it's a tax, it's a tax. So they're going to have to reduce that. So now that is a major loss for anybody who already invested in the technology, assuming that there was going to be that increase in price. So this is like the same way that you have an inflation-linked product, that if the inflation rate, if the government backs down from their stated policy of maintaining a stable inflation, so a government backs down from their policy of maintaining a stable increase in carbon price, then that derivative pays off some compensation to whoever bought that. So is that a fair characterization of why you asked the question? And I had to do the work, okay? But that's the motivation, that's the background, okay? But yes, for sure, so this is it's a projected path of carbon. It's a policy path. Of course, it could be different, but that's what you announce, yes? A lot of countries do what?
They rely on oil.
Oil, yes.
They rely on carbon assets to
Right.
economies are carbon data,
Yeah.
like the Middle East and Saudi Arabia.
Sure. So you say that they can make.
Go back to the different path. Instead of putting prices on up, you could make them very down so they
Right. And then it's incumbent upon the, so if now this leads to much more emissions than before, then the government needs to adjust the price of carbon and say, okay, to compensate for that is the global policy that matters, right? So if now one component of the price is going down and people continue to emit, then you need to compensate by jacking up the carbon price, the tax on carbon. But that needs to be the announced policy. We want to make it expensive to pollute. If with current prices, this price of carbon is what's necessary to reduce emissions, then you maintain that price. But then if some quasi-criminal organization manipulates the price of oil to drop it artificially so that you can continue emitting at a low price, then the response should be to increase the other component, which is the carbon price. Okay. So here are, based on that projected path, which is an average of what many policy recommendations are, in 2015, how much the countries were away from what the price should be. So this is the gap. So China was far away, had a 90% gap. Russia has, for example, a 100% gap because by that point they had zero price of carbon. Canada, was 35% of the way to go into that price, and with Justin Trudeau, they closed part of that gap and have to continue moving in that direction. But they face stiff opposition from many provinces, but Justin Trudeau was just re-elected on the promise to continue on the path of increase of carbon. We had an imbecile for premier in Ontario that to prevent that from happening, start using government money to put stickers on every gas pump around the province with misleading graphs of the increase in carbon price so that people would get scared and let's not vote for the government. So many people analyzed the graphs and they could say that it was just not the total cost, and it was not also including the rebates that the government was going to do, right? So it was a completely misleading campaign with government money, but that was defeated. The Liberals won and are going to continue improving that number. And you see countries like Switzerland have a very small gap, so they're implementing carbon prices that are consistent with the recommended path. Okay, so this is again just to fix ideas. And so, by the way, does anybody know what the range of prices are? It wasn't the previous slide, but the same way that we wanted to put orders of magnitude for the emissions, what's the order of magnitude of carbon price? That's at the low end. That's very cheap, but it could go up to 100. So that's you see that's well, we are here now, so about 50, 100 should be about 2020, and go all the way up to, yeah, $300 per ton. That's the recommended corridor, okay? Inflation adjusted. All right. Very well. Now, this is just showing, as I said, the backstop technology. So that's that thing that it's a model to go down, but you could try to invest more and see if it goes down even faster. But this is some examples of drops in price of different energy sources. So it's like a 14% drop for bioenergy in 1 year. So that's a good exponential decay. And the cheaper it gets, the more can be spent in abatement and the more emission reduction you're going to have. It's the ratio between the carbon tax and the backstop, and you would like to make that ratio as large as possible, okay? Questions? Good, so now we move to the second cycle. So there's an emissions module. What comes into the start of the emissions model is the Y0. Then there's that whole slide, depending on how much reductions are there and blah, blah, blah. And what comes out of the emissions model is E, the total emissions. Now, E enters at the start of that vector there for the carbon cycle. So there's a carbon cycle here. And the carbon cycle is just a layered hydrodynamic cycle of, so there's the oceanic, the deep ocean, the upper ocean, and the atmosphere layer. And this is what geophysicists do for a living, how these things move from one layer to another. And so there's carbon going up, carbon going down, but the deep ocean serves as an overall carbon sink. So there are all these coefficients that you have to estimate. The things that don't have C's in them, they are the stable coefficients that can be estimated from billions of years of geophysical history, and they have to do with how fast these layers can absorb carbon from the other layer. So that's the thing that is very hard to modify. This is a hard physical process, but of course they get multiplied by the actual concentration. So the concentrations are the C's, right? There's some typos, but it should be CO2. All the C's should be CO2. So those are concentrations in the atmospheric layer, the upper layer in the ocean, and the lower layer in the ocean. And there's a diffusion that goes on. So the phi's are the diffusion coefficients, which are physical parameters, but they get multiplied by concentration. So as concentrations go up, there's more diffusion going from one layer to another, and so on and so forth. And the idea is that this is the thing that takes, it's a decades-long cycle for some amount of emissions that come in, but eventually it all diffuses and it goes to the same proportions that you had in pre-industrial levels. So once emissions stop, suppose you stop emissions at some point, they're going to continue to diffuse, and of course they're not going to disappear, but the proportions in those three layers are going to be the same as the proportions that you had in pre-industrial. They're going to be higher amounts, but the proportions are the same. So that's the geophysics of that. But why is then carbon concentration important? So the outcome of the carbon cycle is this carbon concentration in the atmosphere, because it enters this, that's the greenhouse effect. So the amount of carbon in the atmosphere affects the radiative forcing of the planet, which has to do with how much the difference between radiation coming in and radiation going out. So I'm collaborating now with atmospheric physicist at the University of Utah, and he was explaining the actual interactions, and it goes down to the level of quantum mechanics. It's an extremely complicated process that gets simplified as just saying, oh, it's just like a greenhouse. You get radiation coming in, but there's the glass in the greenhouse prevents the radiation going up, and then that gets trapped. But there's a very complicated chemical, quantum mechanical process that goes on in there, but it crucially depends on the amount of carbon, and it's dependent on this, so it has this exogenous, again, radiation forcing, and then the industrial one. And in the industrial one, what matters is the ratio between the carbon that is at the atmosphere at a given time and the amount of carbon that was there in pre-industrial levels. And then, crucially, this ratio then gets multiplied by this constant, which is this sensitivity, is the carbon sensitivity that will say, you know, how much a doubling of the concentration affects the forcing, the radiative forcing. And there are estimates for that, and the estimates are you know, some are more reliable than others. That's the alpha that you're talking about this morning, Marco. And now I learned that people like Marcel Nutz are working on using financial math methods to estimate this parameter. So there's plenty of opportunities for people like us to contribute to this area. But so this will output the amount. That's, again, an exogenous process. And this one then depends on the carbon concentration. So this entered the radiative block. Radiative forcing. And then the radiative forcing then spills out what that F is. So there's all systems of differential equations, couple systems, but the coupling is not like all equations connected to all others. So you see that there's some path that these variables follow from connecting. So it spills out this F, and F now has, so for example, this is the graph for this exogenous radiative force, and is expected to plateau. Now then it comes to this temperature module. Which is the greenhouse process. So there's also a kind of a temperature differential between the atmosphere and the upper layer in the ocean. That's the TLO for the lower atmosphere. And there's basically just a conductive heat process here with this F as a forcing term. So the higher the F, the higher the final temperature after the emissions stop, the higher that temperature is going to be, okay? And then, so that's two more equations there. So you can count, you know, don't remember, but there's a bunch of equations here, but they're all sort of exogenous equations except for the emissions. There are three equations here for the carbon cycle. There's one equation here for the radiative forcing. There are two equations here for the temperature, so that keeps adding up to the system. And then what it comes out here is this T, so that's the temperature anomaly, the temperature above pre-industrial levels. And then T is an input to the damage function. And the damage function is the most controversial part of this whole cycle. Everything in each of those boxes has good estimates. Now we enter a completely uncharted territory, because even the definition of the damage function is hard to articulate. You need to say, what is the output that you would have? What is the decrease in output caused by climate change compared to the output that you would have in the absence of climate change? But how can you possibly see the output that you would have in the absence of climate change? Climate change is all around. It is affecting everything. So it's a very hard counterfactual. It's a very hard hypothetical thing that you need to compare with. And economists have botched this for many, many years. And so the best thing that you can do here is do educated guesses, unfortunately. But you have, because it needs to be part of the model. But you have to do educated guesses with the damages. So for example, Nordhaus postulates that the damage, he used to think that it was like that. Now he's going for an even simpler one. He's saying it's just quadratic. It's not 1 minus 1 over quadratic. It's just, what the hell? Make it a quadratic function and estimate the coefficients. And then other people have suggested that damages, so that's why that superscript is, that the damages, a proportion of that should be allocated to capital, and a proportion of damages should be allocated to output. And then the type of so this is a difference different proposal by Stern and Dietz. This is another way to introduce damage in the system, not directly by affecting both output and capital, but by affecting productivity. So it's the idea that, you know, workers and machines, they become less, workers, because that is only for workers. The effect on them, on capital, will affect machines, but in addition to that, workers are less productive. Imagine have to work in a very hot environment without the air conditioning. You know, we got here this morning, and without the air conditioning, Lane would not be here for the talk. So imagine that, you know, collectively, how much productivity we would lose. Cannot imagine. If Lane cannot be participating of things, we would be all less productive. Anyways, the actual points here, there's dots, these are what people say that they have observed in terms of damages. And all the others are curves that, so this is the Nordhaus curve that is just a quadratic with a tiny, tiny coefficient. So it's a quadratic with a very low increase. Eventually, this looks like a quadratic function, but this is the bottom part of a quadratic function, okay? And these are other damage functions proposed by other people. That's the guy who killed himself, Weizmann, in that light green damage function there. So how does Nordhaus obtain this? Well, he just fits a quadratic function to those points. But how are the points themselves obtained? So another of my collaborators, Steve King, I sent this graph to him, because I'll explain to you how we produced that graph, but the other functions were produced by my students, and I said, look, you know, this is what we got by fitting these curves to these points, to these data points. And then he replied saying, yes, except that they are data points in the same sense that I'm a Norse god. And Steve is very ugly, so he's not a Norse god. So what he means is that these are really not data points. And he has an entire talk that he's given now, it goes to the OECD and other places, showing how there's a lot of corruption in these data points. First of all, they're not all independent points. They refer to studies by themselves, so they look like more points, but they are all coming from the same source. But even when you look to see what the source of the points are, here's what they're doing. So remember I said, how do you estimate something in the absence of climate change? So what they try is to look for locations that are in all respects, all economic respects, identical. So they have the same labor force. So for example, 2 cities in the United States, you know, the same composition of the labor force, the same access to markets, the same technology around, the same transport network, except that one city is hotter than the other. And then they see, you know, what is the decrease in output, what is the decrease in GDP for that city caused by the temperature. So that's not really climate change. That is just the effect of temperature on economic output, controlling for all the other variables. But it's not really what you're looking for, which is how would the economic output of everybody would change if the temperature in all locations went up or down. So this is going like immense fights in the internet about that, because the people who promote that view, they say, look, you know, there are places in the United States that are 10 degrees separate, and nevertheless the loss in output of the 10 degrees warmer place is only 20% of GDP. And then other people, real climate scientists, they say, are you effing kidding? You know, with 10 degrees more for the entire planet, not 10 degrees difference between one city and another, 10 degrees more in the entire planet, you would have all the coastal areas disappearing. How can you say that the loss of the entire city of Manhattan to disappear is only 20% of GDP? Right? So that's the kind of cognitive dissonance that is going on in that kind of debate. Every single one of those points was generated by this type of technique. Careful statistical studies that look for very similar cities in all economic senses except temperature, and then extrapolate that to what the effect of temperature would be for the planet as a whole. So if you accept that as a methodology to determine those points, good for you. So this is the kind of thing that Weizmann was rebelling against, and he was saying, no, you shouldn't accept that, and in particular, you should read the climate literature more carefully, and you should see that there are tipping points that happen when temperatures increase. There are, currents that are going to go the other way around. There's the melting of the polar cap that is going to release methane into the atmosphere, and methane is a greenhouse gas that is, 100 times more potent than carbon. So when that gets released, all these calculations go out the window, and the increase in temperature is going to be much higher. So that kind of tipping point cannot be extrapolated from your little idiotic points that you are calculating from one city to another. So the only way to do that is to combine the climate models with reasonable guesses of what the drop in output is going to be at higher temperature when those tipping points are going to occur. So what my students did was they say at 4%, at 4 degrees temperature, if you think that the decreases in output are going to be 10, 20, 30, 50%, you fit a logistic curve like that because it cannot be more than 100% of output that is going to be lost, and you see what those curves are. And then you put those curves into the model because they need to come into the model at some point. So then the damage then affects y, because now you have a y that is the damage times the y0, right? Your y is 1 minus damage times the y0 times the abatement cost. So there you have, this is the whole picture, and in here is the economic model. So what I was telling you about before with the King model is inside here. Everything else is sort of well understood from the point of view of physics until you get to damage, where you need to do this kind of guesswork, but it's an important guesswork. And what I want to impinge on you is how divergent the views of economists are for that guesswork, but you have to have it there at some point. And then if it completes the loop with the economic model. Before I start showing results for that type of model, are there questions at this point? Yes? So that's what that D is. So yeah. Right? So those are those points that are there. And then they say that, if you believe Nordhaus, you can extrapolate from those points and say that at 10 degrees, look at his curve, at 10 degrees increase. Yeah, but the global GDP is hundreds of trillions. So that's of that ballpark. But the point is it going to be trillions, or is it going to be tens of trillions and comparable to hundreds of trillions? So is it going to be 10, 20% of GDP or 90% of GDP? Because if you're now at losses that are 90% of GDP, then yes, then you're back to the Stone Age, so to speak. Year to year. Those are the losses that are happening year to year. So, I mean, Nordhaus is so blasé about this. And you can understand why you can drive someone to suicide, right? Seriously. Like he even wrote a paper afterwards that, with this kind of damages, because this is just saying that by the way, this is damage in 2150 or something, so a time very far in the future, okay? He says, in 2100 and whatever, the GDP caused by a 10-degree increase in temperature is going to be 20% less than what it would have been if there was no damages. But this is 100 years later. So a 20% decrease in GDP after 100 years later means a tiny decrease in GDP year to year. It's imperceptible. So he traced the two curves, not this damage curve, but the actual GDP curves over here. And he says, you cannot differentiate them if you're drawing with a number 2 pencil. So his conclusion is the impact of these damages to the economy is going to be negligible. And he's promoting that thing. The impact is going to be negligible. And he's calculating the optimal path for carbon emissions, for carbon prices, and for whatever. And he even calculates the optimal, because there are some places that are going to be better off because of climate change, because they're going to improve productivity and so on. So he even calculates the optimal carbon temperature increase, which is more than 4 degrees. So these people are like in an alternative universe where exactly 100 years from now, you can have 10 or 15, you can have the planet being 10 or 15 degrees warmer than it is on average, and the economy is just moving around swimmingly and nothing catastrophic happened, okay? So that's the point, is the low point of the talk. It's the most depressive part of the talk, and it drove Weitzman to suicide. I hope it doesn't do anything bad to you. But that's what the majority of the economists are going for, is this kind of very benign projections of what's going to happen. 10 degrees increase on average is causing less than 20% damage 100 years from now. So it's tiny damage that happens year to year. And 10 degrees on average means that there are large parts of the Earth that are going to be uninhabited, because they're going to be like more than 50 degrees temperature in many places that are 40 degrees now. Rio, try to live in Rio at 50 degrees, okay? And then they say humans adapt. We're going to be moving around. We're going to be staying in air-conditioned places for longer. The decrease in GDP is going to be 20%. And you ask them, why? Because we estimated. And how you estimate it? Well, we look at 2 cities now, and they're 10 degrees apart, and the 2 cities don't collapse. You think I'm exaggerating. I can see in your faces they say, no, Matheus cannot be read. Go and read the papers. They all are doing exactly that, okay? It's stomach crunching, stomach churning, it's sickening, the type of thing. Anyways, let's continue. Now it gets better from this point on. I promise that there's an optimistic view to the talk. So yes, I want to show you results of the model. So that's the entire model. This is the type of picture, but summarized in a better way up there. But you can see everything that I just put in that blackboard. So I'm going to deal with 3 different papers. One is the it's a typo. It's AFD, not ADF. It's Agence Française de Développement. So it's the AFD paper. It's called Coping with the Collapse by Bovari, Giraud, and other co-authors. Came out last year. They did a couple of papers. There's one called Coping with the Collapse. The other is Debt and Damages. And so we're going to look at what they're doing. And then we're going to look at what my McMaster team is doing, and then what the FMTC people last summer did. So starting with them, so let's understand these graphs. What's going here is, what is going on? So this is a run from what they call the no feedback loop scenario. So this is a simulation of the model without that part. So just do the model for a given temperature and just pretend that there's no climate change. So pretend that there's no damages. So what they wanted to do is to see, in the absence, what's the baseline? In the absence of climate change, just with the economics and production and debt and profits, and calibrate the functions to what firms are actually doing, dividends. So they did a global estimate of all those things. Now with a separate team, I'm doing local estimates for different countries, but they did a global estimate to see, forget about climate change for a second. Let's see what it would be without climate change. Because if the model without climate change, because that model, that 3-dimensional model, it already admits some collapsing solutions. So if the model without climate change was already going to that, then we're in trouble. That's not climate change that is causing that. There's something fundamentally wrong with the economy, which could be, because our economy has had some, big cycles and upswings and downswings. But what they're saying is the more or less comforting situation that in the absence of climate change, the world is just fine. Because this is, so employment rate and wage share are these two lines. So there's two of those variables, the state variables of the model. They are stabilized into finite values. Like I said, for so you have employment rate of above 70%, and then a wage share above 60%. And this is the inflation. So the inflation rate is going to stabilize at about 2%, which is an okay inflation rate. By the way, a non-okay inflation rate in many of these models is a deflation. The problem is not inflation, the problem is deflation, because it's a contracting economy. This is the graph for output and real output. So you have, so there's real output growth, so it stabilizes at about 2% output growth per year, which is also good, like the economy is going at about 2%. And this is the debt ratio, so it's that little variable D that we said, in some countries is 20, 30, 60, 50%. This is what is going for the entire world, and it's stabilizing at about 1.6 for the debt ratio, okay? Which is not too bad. England now is more than that, so clearly, economies can survive that. The worrying numbers for debt ratios, now think about the entire private sector as a combined balance sheet. Debt is the liability. What is the asset? It's capital. If the debt is higher than the capital, then the entire private sector is insolvent. And what did I tell you that capital is compared to output? There's a quiz. I told you this number before. What's the capital to output ratio? How many times is capital larger? 3. Capital to output ratio for most countries fluctuates around 3. So your debt to output ratio could potentially go up to 3. If it gets to 3, it means that the private sector has no equity. It has as much debt as capital. Of course, 1.6 is bad, but there is still a lot of equity here. So there are no generalized defaults. But the threshold that you need to keep in the back of your mind is that if it gets close to 3, then you're in trouble. Okay, this is the actual output. So that was the output rate. This is the actual output and emissions. So both output and emissions are growing. So emissions are going to up to 160 gigatons per year, which is 4 times what they are now. But they are not being controlled here because it's without feedback. And the output continues to grow. And this is the temperature increase. So the temperature with no feedback, no policy, no nothing, it's expected by 2200 to be 8 degrees warmer than pre-industrial level. Okay? So that's your base case scenario, no feedback. All right. Now, the second, so I'm moving in steps. So the first step is just to say, ignore all of this. So just concentrate on that. And the message is, we're fine. Now, of course, there is climate change. And the whole model would be dynamic in each of those blocks. Yes? Yes, because remember there was that equation for population, which is logistics. So the population growth also stabilizes at around 2050 at around 8.5 billion or something like that. Okay? So first thing I did is just look at the economic model, and we're fine. Now, we could go dynamic, and we are going to go dynamic for each of those blocks, and all along is a differential equation system. There's an instantaneous effect on the economy, but you could play the following game. We know that this thing here is going to stabilize at some point, that all diffusion with the different layers in the atmosphere. So let's just wait until this part of the model reaches its stationary point with temperature, and forget about the simulation of the entire model. So do a shortcut on the simulation. So sever the model in here, wait until the temperature stabilizes, and only feed back the temperature in here. So shortcut by only feeding back the final temperature to the economic module, okay? So you understand the shortcut that we're taking? Where's the thing? It's there. I see it. Then, this is what you do by just inputting the final temperature in the economic module itself, through the damage. So ignore the intermediary steps, just input through the damage. And what you have, so this is remember the three variables are the employment rate, the wage share, and the debt ratio. And you see that for low enough increases in temperature, so no changes from pre-industrial level up to 1 degree, so all this part here, the new equilibrium that you find is close to what the old equilibrium was. Of course, it's different, but there's a kind of a smooth relation with temperature, okay? And in particular, the debt level is increasing, you accumulation more debt, up to a certain point here where something strange happens. You move from this to there. So that's a bifurcation. That's a bifurcation caused by this temperature increase because the model, the underlying model, has two stable equilibrium. Has the interior equilibrium that you've been following along here, but it has another equilibrium, and at the point where the temperature is high enough, you do bifurcate. So this model does what it's impossible to obtain in the Nordhaus model, which is continuously smooth variation with the temperature, and that's why he never gets this collapsing behavior. So this model does show a collapsing behavior for a high enough temperature. It bifurcates to there, and there happens to be around 4 degrees. Everything in the model is estimated with actual variables, so this happens to be around 4 degrees, which is what the climatologists say is one of the tipping points for all these other climate bifurcations that occur. So we are seeing here an economic bifurcation happening at the same temperature that the climate bifurcation has. And that's why I tell you it's a much more compatible model with climate. Yes?
It's not clear for me. So you are not using the temperature, the damage function.
I am, but only at the last step. Huh? This one uses the mildly, the Weitzman, not the Nordhaus. No, because the Nordhaus has 2 points in the model. That's the low damage function and the fact that there's only one equilibrium. This model has multiple equilibrium, and yes, you can make the damage functions more severe. But it's the combination of the two. I'm going to show you a picture where even with this model, and if you use the Nordhaus damage function, you still go to the good equilibrium. So you're right, it's the two things that are happening here. First of all, the model has to allow for a bifurcation. If it's never there, then you're never going to find it. And the DSG models, even prior to Nordhaus, the DSG models don't have that. So you're never going to find that in DSG. But now in a model that allows for bifurcation, you need to have a severe enough damage function to actually go to that bifurcation. So that's right. Okay? So here's perhaps addressing your question a little bit more. So this was just the effect of the temperature. So I said, short circuit everything else, just look at the final temperature and see how it affects the system. But now let's just do the full dynamics, the full transient dynamics, and see what happens. So that's shown in here. We're going to go section by section of these graphs, but in each of them there are different curves. And then the blue curves, you cannot read that, but the blue ones are the base case scenario, the one that had no climate feedback, and the Nordhaus. So the Nordhaus is the slowly increasing damage function. And you can see in each of them is that, there are two curves there. You can't see, but there are two. And they are, the Nordhaus and the base case, they are very comparable. So yes, even in a model that allows for a collapsing equilibrium, you don't approach that collapsing equilibrium if you really believe that the damage function is an extrapolation of the points that you've been observed of damages so far. So if you believe in that, go ahead and sleep well, and you're going to sleep well for the next 100 years or so. But if not, if you allow for a little bit more convexity in the damage functions, then you start seeing this, and then the more convex the damage function, the more pronounced the effect is, the earlier the effect is. But you can summarize the whole story by this one, which is real output. And it's when, so output increases until emissions are too high, and because emissions is too high, it goes through the cycle, the temperature is too high, it's going to have damage to output, and the damage over overtakes the exponential increase and it starts to flop. And once it starts to flop, because now there's a lot of debt, if it was a model without debt, who cares? You just have a new level of output. But because there's a model with debt that you have to pay for previous commitments based on continuous production, if your production gets too damaged, you cannot pay, your debt sort of overtakes your production, and then everything collapses. And that collapse can occur at different stages depending on the damage function that you put there. But crucially, the date for that is within the range that the limits of growth had predicted. So our model is going back to the simple predictions of the limits to growth. This is the output rate, so it's just the rate at which this is increasing. And obviously for these curves here, they go to a constant rate, and for the ones that are collapsing, the rate goes to a negative value. This is the private debt ratio, the little d, and for the Nordhaus thing, it stays there below 2, but then for all the other curves, it goes up, except for this one that also stabilizes, but it stabilizes at a high value. I think actually these are the two curves. Yeah, that's the baseline scenario, that's the Nordhaus. So the only thing the Nordhaus does is to have a slightly higher debt ratio, but what you see in the other curves are debt ratios that either go to infinity or are much larger than the 3 threshold that we talked before. And this is the inflation rate. As I told you, inflation in this kind of model, they're bad when they go negative. So in the baseline scenario in Nordhaus, you have positive and constant inflation. In all the other ones, when you have real output going down, then inflation, it becomes a deflation. There's a debt deflation spiral that had been predicted by Fisher, among others, in the 1930s. Okay? And then the final thing that they do in that paper is, it's in the second paper, they do an extensive sensitivity analysis with respect to some of the parameters of the model. There are, for example, the doubling coefficient and so on and so forth. So they calculate these ranges of values. And you can read in the paper, they calculate if they want to remain both below 2 degrees for the temperature and 3 for the debt ratio, what are the probabilities that neither of these two thresholds are going to be reached based on the distribution of the parameters and the result of the simulations. And there are tables in the paper, and I think, then they do here with the no policy. We're going to talk about policy in a second, but with the papers that I'm doing, because I have more familiarity, but they do for no policy, the carbon policy, and government subsidy. And they say that, if you don't do anything, then the chances of remaining below the 2 thresholds that you want are minuscule, so less than 1%. But if you implement a sufficiently steep carbon tax, and in addition to that, you put subsidies so that the debt burden of the private sector is not that high, then there's about 1 in 4 chances that you can be below those two thresholds. So 1 in 4 is still worrying, but it's a fighting chance for humanity. It's much more than 1 in 100. Right, so that's the optimistic, if you like, message of the paper. If we do the most aggressive policies, then we have a 1 in 4 chance of actually, seeing this through the increase in emissions and maintaining temperature below the catastrophic thresholds. So again, maintaining my line from the beginning of the talk, it's damn difficult, but it's not impossible. There is a chance, but there's a lot that we need to be doing. Now let's just continue a bit more. So I want to move now to what the people at McMaster are doing. So I sent 2 of the students to IFD in February this year. They spent 2 weeks there collaborating, looking at their data. And then the question was, what can we do that you haven't done and you would like some dedicated team of students doing? Because you're busy, you're doing other things, you have to report to organizations and so on. So what can we do? And they said, by far, because this model has many extensions that you can do. You can have a better consumption function, you can have this, you can have that. So it's already a complicated model, but there are many ways to extend it. So they said the one extension that we're interested in is to separate the world in 2. Because even from the first agreements on climate dating back to the 1990s, there were already the separation of sort of developed and developing countries. And the fact that, the emissions are primarily done, have the cumulative emissions were primarily done by developed countries, but they are achieving emission rates that are much better now, Germany or so on. And it's the developing countries that need to catch up. And in order to catch up economically, they need to have emission rates that are much higher. So right from the beginning, it was seen that there was an asymmetry here, that if everybody says, oh, whoa, stop emission, well, that would be completely unfair, because the rich world already benefited from centuries of emissions and achieved a certain standard of life, and the poor world, you're now saying, no, you're denying that. So there needs to be some transfers. There needs to be some inter-regional transfers here to allow for dramatic abatement costs in the developing world, so that they still can have economic development, but with sufficiently low levels of emissions. So they said, you need to put that in. You need to put 2 regions. But as soon as you put 2 regions in this economic model, all sorts of strange fluctuations happen between the 2 regions. There's fluctuations in employment, in the wage share. So it becomes so at the core, this is a predator-prey system. Now imagine a predator-prey, so it's a predator-prey system that we're putting all sorts of other variables on top. But the core dynamics is predator-prey. Now imagine that you have a 2x2 predator-prey with an interaction mechanism, which is this transfers and the temperature. So you can imagine all sorts of the system feeding off of each other. So it's a much more complicated predator-prey dynamics. And then the auxiliary variables. So this is the type of things that we see. So this is your 2 predator-prey systems moving together with the fundamental variables, the wage share and the employment, and the debt ratio and the capital. So again, you can have sustained oscillations like that, but there are many ways in which just the economic system can collapse by itself, and we haven't quite determined what are the sort of parameter regions there, because it's very arbitrary how to separate the 2, the north and south. So we're still doing a lot in that. We haven't answered the IFD question, but that's work in progress. The other thing that the group at McMaster did was for Canada, so we wrote a little white paper for policy, the different scenarios, no policy, low carbon, high carbon, low carbon with government subsidy, what actually happens in Canada with government subsidy and a higher carbon price with government subsidy, and what the path for temperatures are. And you see that they are all above the 2-degree threshold, but the most aggressive one is not too far above. It's like 2.5 or something. But really, yeah, do what Doug Ford in Ontario wants to do, and you're going to be at almost 5-degree increase by 2100 if you follow that policy for Canada. Questions so far? Because now I'm going to move to the last part, which is what the group in South Africa did, and it has to do with sensitivity and some other finance-related matters. Yes?
Yeah. How about kind of
rebellion against carbon taxes, for example, Gilets jaunes type of thing?
Yeah, I mean, that has to be done with care, right? So Macron did the most stupid thing that he could have done, which is, I mean, this is not uniform. It's not like everybody needs to pay the same carbon tax. The point here is to charge the polluters and to subsidize the non-polluters, right? So there is a transfer that needs to be embedded here. In the same way that for region, for North and South, there is a transfer mechanism that needs to be there within a country, and Canada is doing that. So Canada is charging a carbon tax, which is then uniform for whoever does it, but it rebates a lot of the low income, regardless of what they're doing. It just does a rebate for low income. So it uses the revenue of the carbon tax to rebate the cost cost of heating, the cost of fuel, the cost of electricity for low income. And that's the only way to do. And Macron didn't do that. He did exactly the opposite. He introduced a high tax on fuel and gave rebates to the high polluters. Because, industry. And the low-income people got most of the proportional increase in fuel. And then, of course, they need to rebel. So yes, I mean, there's a reason why our friend Villani broke ranks with Macron, is for that type of policy. It's try to be too clever and not doing the obvious thing, which is charge the polluters, rebate the low income. That's what should be done in France. But now I'm getting too much into the political arena. I mean, the whole talk was political.
Anyway, my point was that it perhaps might be interesting to try to incorporate in the model this kind of reaction from the...
Yeah, but that's very hard, right? Because now we're talking about, yes, public opinion and politics. So we're doing it in the realm of, what the policies ought to be, and then the politicians need to implement that in a way that is palatable. It's their job to do that. It's not my job. It's their job not to screw up the implementation of the policy. Maybe if I do like Villani and become a politician, I can help them doing that, but when I'm not doing that yet. Okay. So we'll move to the last part of the talk. I don't think I'm going to go all the way to 12:30, so I'm signaling to you, responding to your signal that I shouldn't go to 12:30, that I'm not going to go to 12:30.
Well,
it's like game theory here, right? We're going to try to get to an equilibrium. Let's see what happens.
let me play my part of the equilibrium game.
And reduce the attendance. Very good. So this is now the FMTC, so it stands for the Financial Math Team Challenge. We have a report on that. We might or might not turn that into a paper with the McMaster people. I'm continuing because I know where they are. But maybe I'll get the FMTC people to help with the paper in the future. But what I put to them in South Africa as a problem was two parts. First, look at the sensitivity with respect to the many parts of the model that could be influenced by finance, which are the convexity of the abatement cost. Remember, for each unit of emission, you have to pay some, and that goes n to the power theta, and that theta you can reduce by investing more in R&D, by having better technologies, cheaper technologies, more readily available. Second was the price of the backstop technology itself, so the reduction rate in the price of the backstop technology. And the third was the ways of financing. So in the same way that the people at IFD, they consider government subsidy, so these kids, they also consider government subsidy, but they did something else that the IFD people hadn't done, which is, so remember when I talk about green bonds. So green bonds are a way to incentivize the private sector that wants to invest in this type of projects, to divert funds to this type of projects. So you can break it, because now the point is that, if it wasn't for green bonds, then companies would have to raise this money in regular bonds. So that's part of D, that's part of the debt level. I'm simplifying here, there's loans to banks, but we could have a version of the model that has bonds. But that's the part of the debt level. The green bond innovation here is that they can finance that cheaper. So the whole point of issuing a green bond is that there's a green bond premium, because there's higher demand for that type of bond, because people want to feel good. They want to invest in bonds that are helping the economy, so they're accepting to pay a higher premium. Accepting to pay a higher premium means that they're going to be receiving a lower interest rate. So the variable that we model here is a spread, is an interest spread between regular debt, bank debt, which is in the model, and suppose that part of the abatement cost, a fraction of the abatement cost, can be paid with green bonds. And those green bonds now have a premium, so they have an interest rate differential, an interest rate spread. And look at that interest rate spread as one of the sensitivity variables for the model. So do you follow the logic? Okay. No question. So just like the IFD people had a baseline model, they did a baseline model too. These are the variables, the value of the variables for 2,100. And you can see that's the one that we said, yes, it sort of works, right? So what is this? GDP is increasing. That's emissions. Emissions is at some point going down. This is the temperature. It's at some point going to 3 degrees, and that's the debt level. The debt level stabilizes at 1.7 or so, so it's below the 3 scary threshold. So again, confirming what the IFD people have found, that the baseline without the feedback is a good scenario. So you could have sustainable economy. Okay, now. they do so that was the benchmark scenario. Now, again, like the IFD, they do a scenario with, what is this? No, that's the bank, wait. Did I not put? I copied the same graph. I just changed the title, but I copied the same graph. The graph that you should be seeing here is for a collapsing one, just like the IFD finds. So with no policy, no carbon tax, no anything, then emissions continue to rise, and there's a decrease in GDP. So sorry, it's not the correct graph. Now, with that in mind, now they start from the baseline scenario, and with some, I think they do a little bit of tax, so that is not the fully collapsing one. But then what they do is modify those variables that I told you before. So modify the theta variable, which is the convexity and the abatement cost, and modify the, so here's the modifying the theta variable and seeing the impact that it has in the two key thresholds. So the temperature that wants to stay below 2 degrees and the debt level that wants to stay below 3. So you see here that, and these are the different fractions of capital, of damages that are allocated to capital. And what you should see is that it's possible to force this C to go below 2 or close to 2, and it's possible to force the debt level to go down, but you need to have a very high theta, so presumably not achievable thetas just by technology. So this is the estimated value of theta that IFD was using, and we just see that making it 20 times larger will help, but it's very hard to get there. This is for the reduction in my problem again with copying and pasting. One of them should be the reduction in the rate of decrease in the backstop technology. And what it should show is, again, some reduction in the temperature and some reduction in the debt level, but not, significant. So you can do things there, but you cannot change a lot. And this finally was for green bonds. So this is the spread on green bonds. To see anything happening, you need to have like a 200 basis point spread from green bonds, which you're never going to see. So that was, this 3 can be possible to be improved by financial innovation, by technological innovation incentivized by finance, and they go all in the same direction. So of course you should be trying to do that. The more green bonds, the better convexity, and so on and so forth. But they are not going to solve the problem by themselves. So the things that they did do that show that make a difference is, again, carbon tax, and a carbon tax combined with a 50% subsidy for the government sector, which is similar to the numbers that we're actually seeing, that all the investments are half private and half government. So if you do that, then yes, your debt ratio can remain in in acceptable values, and your temperature increase, well, it's slightly above the Paris Accord, but maybe we can live with that. That's away from the 4-degree temperature that we started to see many of the bifurcations. So that's the positive part that I was saying, that you have to be aggressive, you have to do those things. Finance can help, but cannot solve everything. And then the last thing that they tested was, okay, so carbon tax is what this is. So you fix the price of carbon in a trajectory, and then from that, the firms determine what's the optimal amount of reduction in emissions that they will do. That was in one of my initial slides, okay? But what if you want to do cap and trade? What is cap and trade? Cap and trade is the government, instead of fixing the path of carbon, fixes the path of emissions. It wants a decrease in emissions in a predictable way, and then now you fix the decrease of emissions at a certain rate, you know what the emissions should be, you go to what the reduction has to be to achieve those emissions, and then you deduce what the carbon price has to be. right? So the price comes out as a consequence of the rate of decrease in emissions. So we wanted to see, now put that in the model, would that make a difference? Because some people say, oh, no, tax is tax. As I told you, there's always a libertarian in the room. So why not let the market decide? So put what you want to do for emissions and let the market decide the price of carbon. And we say, sure, go ahead, knock yourself in the head. This is what the carbon price was imposed from the outside. Then we revert that and said to achieve a comparable decrease in emissions, what the market-determined price of carbon would be something like this. So a little bit more smooth, and maybe the market is going to like that, but it's not, dramatically different. It's always in the same ballpark. And most importantly, the temperature control that you achieve with both policies is comparable. So I say to my libertarian friends, fine, do cap and trade, knock yourself, as long as you have a sufficiently steep path for reductions, emission reductions. So we're here, we are in the end. Climate change is the most formidable challenge faced by human race, no doubt about it. We have not faced a problem like that ever because it involves everything that we're bad at. We're bad at projection to the future. We're bad at discounting risks. We're bad at evaluation events with low probability. Every single human trait that we're not being prepared for is coming to play in here. We are bad at coordinating policies. We are bad at doing international transfers and collaboration. So it will require that we go against every single instinct that we always had as a species. Traditional economics is beyond repair here. Well, I made the point throughout the talk of why. So what you need is a dynamic model that deals with disequilibrium within the economic variables themselves and slowly adjusting variables to couple that with the climate model. Finance is likely to play a role because you need a functioning financial market and functioning banks, because you need debt, because you need to maintain these debt levels at sufficiently high levels without too much bankruptcies and so on. And it can help with carbon tax subsidies, green bonds, green securitization. So what is green securitization? Many of those projects involve small communities. Small communities are going to be doing cleaner water plants and this and that. And they're not going to be able to sell a green bond for that. It's not attractive enough for that small project. The return is not good enough. But what do? You pull them together. You securitize, and then you sell those to green investors. So that can be our sort of redeeming contribution to the world. We screwed up mortgage securitization. We can help with green securitization. Green central banking. Mark Carney had a speech recently, the governor of the Bank of England, where he was putting that front and center, that, when you calculate capital ratios for banks, there are these factors that you multiply to the different types of loans or different assets that the banks have. So a central bank can immediately spur investment in green finance just by applying a zero weight to green bonds or green assets, just like they do for government bonds. Or if not zero, much reduced than from other assets. So that will there's nothing that the banks care more as the cost of capital. So go exactly where they care more. And they're going to be lending more to this type of projects. And so on and so forth. So what I'm saying here is that throw all that you have. This is a problem that's going to require everything that you can possibly put your ingenuity to. So I spent lots of time and effort in my previous work talking about bubbles and what creates bubbles and how they should be avoided because they cause havoc in the economy. But my friend Bill Janeway works in venture capitalism, and he says that bubbles are both banal and necessary. Bubbles happen all the time, and without bubbles, you don't have the type of creative investment. You would not have, you would not have telecoms, you would not have, because you cannot operate within the confines, again, traditional economics of just risk return. If you don't have the crazy people doing this completely irrational types of investment, like .com, then you would just have mediocre investment. And he says, so this is what's called, so then, of course, there's the downside of the bubbles, a lot of dislocation and people losing money, but that's Schumpeterian waste. So Schumpeter would say the concept of creative destruction, and all the, again, libertarians and tech people, they like that. And Schumpeterian waste is something that we should be prepared to accept. We should be prepared to accept the downward consequences of an upward bubble. What you should not be prepared to accept is Keynesian waste, is that during this downturn, you have idle resources just because the government, which is the agent that can do that in the downturn, is not investing. So there's a big difference between Schumpeterian and Keynesian waste. And here I'm saying, now I'm agreeing with Bill, it's not just that they are banal and necessary, they are going to be fundamental. We need a green bubble. We need people to be exactly euphoric, irrationally exuberant, and wanting to invest in green, even if this is going to collapse later and a lot of people are going to lose money, because the type of technology that is going to be created is just like the fiber optics during the .com bubble. They're going to remain there for the next phase of necessary development for the green economy. Okay? So that's why when people like Greta Thunberg goes and makes speeches, I say, yes, that's exactly what you want. You want that kind of urgency. You want that kind of sense of panic to get people fired up to do that, because that's going to be absolutely necessary. So perhaps more than at any time, the future of the world is in our hands, and well, I hope we do the right things. Thank you.